solution method for FODE. So for the given, FODE, your objective is to get the solution, right? You want to get solution. So in a big picture, we have three different types of solution method. Okay, methodology to get solution, right? The first one will be graphical or graphic method. Okay, that's the first category, type of solution method, right? And second one is numeric method. Numeric or numerical is the same thing. Okay, and third one is analytic. All right. So graphic and numeric, that's 1.2, section 1.2. And analytic, that's from section 1.3 to the rest. Okay? So the first graphic method is we call it direction field. Direction fields. Okay? The method name is actually the direction field. And numeric, for the numeric, that's it's Euler's method. The genius mathematician, or physician, Euler suggested that method. And analytic, that's the thing that we're gonna spend our most of the time for this method. Okay, how to get it according to the the different types of solutions. So we're gonna dedicate a whole lot of time on this. But before we move on, we're gonna learn these two methods now today. Okay. So briefly, very briefly, this is direction fields are graphical method, meaning on the graph. We just put it onto the graph. Since y prime it's a slope, right? In explicit form, that's a slope. So we just take it and we just draw the slope in space. Okay? We just as many as slopes at points in the space. Then that'll show you some flow of the solution curve. That's a solution function. Okay, so graphically you're having the overview of the solution. That's what direction fields are. Okay? We're gonna learn it in more detail. And that's a whole overview of that graphic method. And what about Euler's method? This is kind of approximation. It's approximation using iterative way, meaning keep calculating repeatedly, okay, and then you get to the solution. So it's more appropriate for the computer, right? So that's the numeric method. We usually, computer we refer to numeric method, right? And analytic is a total subject from 1.3, so we're gonna touch it later on. And I already uploaded the video lecture for this stuff, so you go back to your home and look at the videos, all right? So today I'm gonna lecture up to 1.2. I mean this numeric point, all right? So that's a very first map of what you're going. And I'm going to give another map, another whole complicated more map for analytic after 1.2, after the explanation of 1.2. All right? Okay. So direction field. It's a method that has been done by noticing on geometric meaning of y prime equals something. So it's a explicit form. When it's explicit form, we notice on the geometric meaning y prime is simply the slope on the plot, right? On the graph. That's what it is. So this is the method that's utilizing the slope, the geographic meaning, and it is approximating the solution with slope. It's a tangent line to the solution. That's slope, right? So for example, with this, we can pick as many as points in space to see the how the solution looks like, right? So let's say, for example, we pick 0, 0, 0. Okay? 0, 0. Then y prime at that point will be 0, right? So 0 in slope-wise, it's just simple horizontal line, right? That's a slope. That's a tangent to the slope, the solution at that point. All right? What about, let's see, this is 1, this is -1, -1, 1. Okay? And how about 1, 0? Then y prime is 1. 1 at 1, 0, that's slope is 1, meaning, around this much, right? That's a slope. The solution has to move tangent to that line at that point. Okay? What about here? And that's 0, -1. So this y prime is -1, right? So -1 is this way, right? And so on, and so on, and so forth. If you keep calculating overall this whole space, then you'll see how this moves, right? So at the end, if you keep doing it, if you draw by the computer or any calculator things, that's what you get, right? And out of that arrows, many arrows, you see the flow of the solution function, right? Like that. Here it kind of separates, right? And it's doing that, right? So you can guess what the solution, true solution, looks like. Okay. This is very simple, very intuitive method. But the thing is, you don't get the equation, you don't get the function here, right? You just know what's going on there, but you don't get function solution. So the function of the solution from this method. Okay, so the importance. This is very primitive, method, but it's very intuitive because you don't need to solve ODE. We didn't solve it yet. I mean, we didn't solve anything, right? We just simply calculating from explicit form. That's it. But it shows the whole family of solutions, how it goes. But not the disadvantage is not function, functional form. You don't get it, right? You simply know, how the solution, might look like. Okay? And that's it. That's a very simple method, and you can practice on your own. Okay, next topic is Euler. All right. It's a numeric method. It's a, by Euler. Okay. It's an approximation of the solution value at equidistant x values with an initial value, x naught, y naught. It's initial value condition, right? So you start from the initial value condition, and you do some equidistant type of stuff, and then try to approximate the solution value. Okay, that's kind of I mean, I don't know. We can understand that, right? So it's a simple calculation. Is keep repeating. It's iteratively. If you express that sentence into the mathematical way, that's what it is. All right. So here we start from x naught, y naught, the initial value, right? And for the next x1, next step, meaning next x1, we add h, the step value. Okay, it's an arbitrary step. You could choose any number you want, but at least it's some number. It's keep adding. Okay, keep adding to the initial value. Then x1 will be, if it's a positive number, x1 will be bigger than x0, right? So you change it, right? And then the y1, corresponding y1, is actually estimating value, right? It's not true y. It's an estimating value. Let me put tilde, as an estimation. So y naught plus the step value h times the function value at the initial position, the functional form, because y prime is f of x comma y, right? Actually, this is slope. Same thing. We are kind of geometrically, we're using that. Okay? Then we get new y1 value. And the next page, we had, x naught plus 2h. This is actually means x1 plus h. So x1 is the previous value, previously calculated value, right? And we are adding the step value too here to get next second, x value. And y2 is actually previous value y1, okay? This is actually tilde. I mean, if you do that, it's an estimation value. Plus, same thing. But the slope at x1 and y1. And keep doing it until, infinite, until you're satisfied. You get it? Let's draw it. Graph will show you more intuitive way. Okay? So we start from x naught here. Okay? And y naught is predetermined. So it's given, right? Initial conditions are given, the values. Okay? And x1 is what? X naught plus h. So this is h. This is h. That's why it's equidistance. Okay? On x term wise, it's same distance, right? And then x1 value is from this, and y1 this, right? Tilde is y naught plus this amount. That's where h times the slope. Okay, because it's a slope here, right? Slope here times this h, and you get this value. All right? And once you get here, you have the same thing. Slope here, right? Slope times h, so you get this value, and keep repeating, okay, until you have same equidistance. So h. Then the true solution. True solution is this. Let's say we don't know, right? We don't know, but let's assume that we know that the true solution. Then this approximation. This is approximation, right? This approximation is following that trend, right? But there's some error. Always, all the time. Because it's an approximation, there should be error, no matter how large or small it is. Okay? Let's go into more deeper. All right? So here x naught and x1, if we magnify, zoom in, in this region, and that was the h, right? H, and at that slope times h will give you a new point, right? But that's not really the true value, so that should be the error of that, at that point. Okay? So the step value of Euler's, so the accuracy, so how close the approximation to the true value, true solution, it depends on the step value h, right? If you decrease the h to here is half, for example, where did it go? If you decrease the half to here, right? For example, x1 is here. This is h over 2, right? But then you're going to have this much. That's y1, right? Then you have, this amount of error. Then this. Okay? But the problem is, if you decrease the h, you need more calculation up to that point, right? It's doubling the calculation. So it's a calculation versus accuracy. So accuracy versus calculation. Computing power, right? So for example, for this, we assume that you know this solution, you found the solution, or somebody gave you that solution. If you calculate using h equals 0.2, this is true value, and this is approximation. That's what you get, right? Let's assume that you calculated everything, okay? And if you decrease h to the half of that, then you're going to have, more steps, right? Because it's smaller steps. But you have eventually, close to the true value. You can easily verify if you, do some laborious work. You can do, Excel to calculate it for you.